Hi everyone, this is Dr. J, and in this video we're going to go through a very simple two-layer seismic refraction problem. So let's get started. So what we're going to have is we'll have the top boundary of the top layer be the surface, of course. So here we are on the surface. We'll have a single layer on top of a single lower velocity layer on top of a higher velocity layer. And the two velocities will be v1 and v2. Okay, just two speeds. It could be 500 meters per second and 1,000 meters per second, or whatever. We'll do more complex versions of this as we go along, but we'll start out simple. We have two horizontal boundaries. So we have a boundary from this kind of assumed infinite medium below, and this layer 1, and then we have the boundary between layer 1 and the surface. Okay. So let's see. So how's our problem look? So we'll give ourselves a sledgehammer. All right, so there's our sledgehammer. Here's our seismic source. And let's draw some seismic waves. Okay, so we know that the seismic waves will be radially spreading out in all directions. And, so on and so forth. The particular wave that we're interested in is the one which is going to travel right along the boundary between V1 and V2, and then, of course, be refracted back up to the surface, and I need to extend my ground a little bit further, and then be refracted back up to the surface so that we can detect it at a sensor, which in our case is a geophone, right? So this is just like what we did in our seismic survey. We have a source, and we have a string of geophones, and this particular wave is getting refracted and then arriving at one of our geophones. It's important to note that the wave that gets refracted at this angle, and this is the critical angle. So let's see. If we draw a vertical line, this is theta C, and it's also the same angle as the takeoff angle, theta C. And actually, I guess I should draw in the fact that this head wave is actually emanating from all along this refracted, from this boundary line. So as the refracted wave continues to travel along that, the critically refracted wave continues to travel along that line, it sends out this head wave, which is what arrives at the surface. And the angle that, this critical angle where we get this critical refraction is actually the same as this angle here, theta C, and the same as this angle here, theta C. So this problem is entirely symmetric. It gets sent out at a critical angle. It arrives at the critical angle because these are horizontal parallel boundaries in this simplified view. It travels along the boundary. It takes off as the head wave at the critical angle, and then it arrives at the critical angle. So again, completely symmetric problem. Okay, so let's go ahead and zoom in on just a single ray and look at the mathematics and what we want to answer is, how long does it take this ray to arrive at the source? What's the travel time? So we have our simpler setup here with two layers, but a single ray coming down. It's being refracted at that critical angle, and then it's received. All right, and again, I'll draw my angles in. And let's put some variable names here. Let's see, so let's call the depth, the layer, call that depth Z. Let's call this distance between the source, and I'll mark some arrows so you can tell which way is the source. Alright, so there's the source over here. We'll call this distance X between source and receiver. And I'm going to call this distance, let's see, I'm going to call this distance dr for d refracted, which is just the distance that it travels along this boundary. Now, of course, again, there's waves emanating from every point along that boundary where the wave has been critically refracted, but we're just going to focus on this one particular ray. What else? We have velocities, v1 and v2 again. v1 and v2. And do we need anything else? I think that's what we need to solve the problem. Okay, so what we want to, again, figure out is what is the total travel time? And total travel time is going to be lowercase t sub capital T for total time is equal to time along section 1 plus time along section 2 plus time along section 3. And we're going to call this, we'll call this section 1, section 2, section 3. And we'll call the distance along section 1 d1. And the distance along section 2 d2, and so on and so forth. And then there's also a travel time t1, t2, and t3. Right, so the total travel time is just the sum of the times of each segment, and the distances of each segment gives you the total distances traveled. So, but what we're interested in is the total travel time. So how do we get this? So speed is distance over time, right? Speed would be like meters per second, miles per hour, whatever. So time then would be distance divided by speed, or by velocity. So if we take distance, say in meters, divided by meters per second, meters cancels out, seconds comes on top, that gives us time. So time is equal to distance divided by velocity. So all we got to do to get the times is take the distance traveled in each section, divide that by the velocity, v1 or v2, as the case may be, and then we'll have the answer. So let's do that. So for t1, let's see, so our total distance d1 is what we want, and we've got z and this theta c. So now if you go back and remember your trigonometry, how does it go with the right angle triangle? Can you guys see this? Nope, I'm drawing off the board. Let's draw over here. So right angle triangle, we have an angle theta. So we have, let's just say A, B, and C. The rule is that cosine of theta equals B over C, right? So adjacent over hypotenuse. Sine theta would be A over C, so opposite over hypotenuse. And then tangent theta would be opposite over adjacent, A over B. If you're not familiar with this, look up basic trigonometry on Google and check it out. So we got cosine theta is B over C. So that's what we're going to use in this case. So if I rename these numbers now, so we're kind of flipped, so the right angle is here. So this is going to be theta c now, and this is z, and this distance that we want is d1. Okay, so cosine theta c equals z over d1. Right? And so what we want is the distance, d1. So then d1 equals z over cosine theta c. All right, that makes sense. So that's d1. And then d1 over v1. So we're going to divide by velocity. Distance over velocity equals time. And the velocity that this ray is going to travel at is the velocity of v1. Okay, so our distance, so our time 1, is equal to z divided by cosine of theta c, that whole thing divided by v1. And we're going to do the same kind of thing for the other two segments. The third segment is going to be exactly the same. And in fact, since d1 equals d3, it's just going to be t1 and t3 are just going to be 2 times t1, and it's just going to be twice this. So what we can say is that total time is equal to, we're going to say 2 times z divided by v1 cosine theta c. All right, and then we have plus t2. So we've got t1 and t3 taken care of for these two segments, and now t2. So t2, it's important to remember that the critically refracted ray is traveling at the speed, and you can see I've drawn the line here just into the second layer. That's because it's traveling at the speed of the second layer. So it's traveling along the boundary, but it's being governed by the speed of the second layer. dr is the distance, v2 is the speed, so the time is equal to dr over v2. We don't really want the dr in there, though. We want to express that in terms of the things that we know. We don't know, what that is. So what we'll do is we'll just take this total distance x, and I'm running out of room to write on the board, but let's see if we can squeeze this in here. So what we want is this distance dr, and that's equal to x minus twice this distance here. So if I bring this line down, right, whatever that distance is, and this is actually going to come back to our triangle over here. This is going to be the sine, or relate to the sine of this theta c. Either way, I'm just going to take x and I'm going to minus off twice that distance, whatever it is, and then that will give me the remainder will be dr. dr is equal to x minus twice something. There's two segments, one on either side, so we're going to subtract both of those out. We'll call this just d x, I guess, for unknown. So this is dx. Bringing our triangle over here, we have z, we have dx, we have d1. We don't know what dx is. We want to solve for it in terms of z and theta c. So tangent of theta is equal to opposite over adjacent. So tangent of theta c equals dx over z. So if we rearrange this to solve for dx, it's just z times tangent theta c. That's dr. So now we need to take dr, divide by v2. Total time is equal to the sum of the time traveled taken by each segment of the ray along its path. We just simply take the distance traveled divided by the velocity of that layer to get the time traveled, which we do for each segment. These two segments are in both in the first layer, so they're velocity 1. This segment is traveling, its speed is governed by the second layer, so we use v2. So these two guys are the same, t1 and t3 are the same. t2 is different, so that's a 2 times z over v1 cosine theta c. That's the first segment and the last segment. And then that middle segment here is x minus 2z tan theta c divided by v2. Okay, so this expression is an expression for the total travel time of the ray during this path. Okay, so now we've got this equation. It's a little bit messy. Let's see if we can simplify it at all. So we've got x over v2, and then we've got plus 2z over v1 cosine theta c, and then we've got minus 2z. So we've got these two z's showing up, and then we got here, I'm going to say sine theta 2 over v2 cosine theta c. So now you're starting to see a little bit of the symmetry of the problem. So we've got 2z over v1 cosine theta c minus 2z sine theta 2 over v2 cosine theta c. These are looking a little bit similar. And then we've got this x over v2 here. X over v2, that's going to stay the same. Sorry, I'm going in and out of the camera here because I want you to see the screen really well. Hopefully it's not too distracting. Plus 2z divided by cosine theta c. So we're just going to take the 2z over cosine theta c that's in each one of these two expressions now. We're going to pull that out. So we'll need to add some parentheses here. And then we have 1 over v1 minus, let's see here, sine theta c. Sorry, that should be theta c there. And v2. We're just rearranging this expression here, trying to simplify it down a little bit. Alright, so now we have x over v2 plus 2z over cosine theta c times this 1 over v minus sine theta c over v2. Alright, so let's see what we can do with this. Okay, so now to take this to the next step to simplify it, what we need to do is focus in on this expression here. And the key is to remember that one of the forms of Snell's law says that the sine of the critical angle is equal to v1 over v2. So you can see we have sine theta c over sine theta c right here. We also have v2. So what we can do is we can rewrite one of these in terms of the other one, and then we'll use that to simplify. So let's do this with v2. So we have v2 and v1, or v1 over v2 is equal to sine theta c. So if we add a v1 on top and bottom, right, we can multiply and divide by the same same value, and it won't change the answer. So we have now v1 over v1 times sine theta c over v2. We'll take the v1 and the v2, and that's going to give us a sine v1 over v2 is sine theta c. So now we'll end up with a sine theta c squared, and we still have a v1 on the bottom here, but we also have that here, so we're going to go ahead and pull that out. So I'm just going to take what's in this square here and rewrite it, what's in the parentheses, and so we'll end up with 1 over v1 times 1 minus sine squared theta c. So do you see how this works? So we're multiplying, dividing here by v1, so this v1 over v1 is 1, so we can do that. And then we have v1 over v2, which is equal to sine of theta c. So then we have a sine of theta c squared over v1, and then we have this 1 over v1. We pull the 1 over v1 out, just basic algebra, and then we have 1 minus sine squared theta c. Okay, makes sense? And then this is, of course, if you remember from trigonometry, this is one of the most easy formulas to remember. This is just cosine squared of theta c. So this is going to be cosine squared of theta c, and you probably can't see this because I'm probably going off the screen. Let's turn a little bit so you can see. Right, now I'm knocking things over, things going crazy. All right, so 1 over v1, 1 minus sine squared theta c, that's equal to cosine squared of theta c over v1. And now, this is very nice because we have a cosine squared theta c here. Coming back over here, we have this cosine theta c in the denominator. So I'm going to erase all of this and rewrite it. So this is the expression, and this is what we're looking for, right? This is an expression which gives us the total travel time. But now what does this look like? Because what is this? We have something equals something plus something times x. This is the equation of a straight line. X times its slope in this case is 1 over v2, plus a constant. This is the same thing, the same exact thing as y equals mx plus b. And I'm sorry I've written the constant first, b plus mx. Constant plus slope times x. This is the equation of a straight line, where instead of y, which is what you might be used to thinking about, we now have t. Here's our graph. You're used to thinking about x and y. In this case, it's just x and t. But if we plot the time of arrival at the geophones versus their position or their distance from the source. Okay, distance from source, and t is the arrival time of that first arrival. So remember, we're talking about p waves. Those are the first waves. They're the primary waves. They're compressional waves. P waves are the first arriving waves. The time of the first arrival versus the distance from the source is going to give us a series of points at each one of our geophones, and of course our geophones are all spaced evenly apart. It doesn't really matter if they weren't in this case, it would still be the same relationship, but that helps us to kind of see the line a little bit better. And we plot these lines. Now, of course, there's a certain distance that you need to get a refraction, right? This is the critical distance. So there's some distance at which you need for refracted waves to arrive at all. And then there's a second distance called the crossover distance, which is when the refracted waves beat out the direct wave. So I didn't draw the direct wave on that diagram before, but the direct wave is the one that travels along the surface of the ground. At some distance, the refracted waves reach the sensors before the direct wave does, and that distance is called the crossover distance. So there's some things that are going on here basically in these near distances, which I'm not going to talk about right at this moment. But basically, once we go past that crossover distance, these points should all line up on a straight line. The slope of this line, if we fit this line, black are the observations. We're going to fit this line, and the slope of that line we're going to estimate is not v2 actually, but 1 over v2. 1 over v2. Right, so this is this slope of that line. And then there's going to be an offset here, which you can see. And that's going to be this constant term. That's going to be the intercept. So that's going to be just 2z cosine theta c over v1. So we're already going to have the velocity of the second layer just from looking at the slope of these points that are beyond the crossover distance. For points that are less than the crossover distance, DC, in this case DC stands for crossover, and you've probably noticed if you've read the book that those points have a slightly different slope. Maybe they look like this, and I've not drawn the line very well because it should be going through the origin, and they're not, so maybe I need to draw the origin. Okay, this graph's getting a little messy now. The point is that these dots here, these points, if we measure the time and distances, and we plot those on this graph, those are going to have a different slope than this line, and that's because those waves are traveling through only the first layer. Those are the direct waves. So geophones that are lying within the crossover distance are receiving the direct wave at the same time or before they're receiving the refracted wave. And the crossover distance is, of course, the time when they're the same. The critical distance is the time at which the refracted wave and the reflected wave have the same travel path. So the slope of this line is going to be 1 over v1. Again, 1 over v1 is smaller, so, v1 is smaller than v2, so 1 over v1 is actually bigger than v2. That's why it has a steeper slope. So from this, from these two line segments, we can get the velocities of the two layers. And then from this intercept here, we can use the velocity in layer 1 that we've estimated from that slope, use the velocity in layer 2 that we've estimated from that slope. Actually, I guess we don't need v2 for this intercept. For this intercept term, we can work out what the depth to that interface is, because we know what theta c should be given v1 and v2, and then of course we know what v1 is. Alright, so we know what theta c is. We could substitute this into here if we wanted. Either way, we can get everything, we know everything about this intercept except for the depth to the interface. And so we can solve for what that is, given this intercept value that we measure, using the two lines that we've fit. So what have we done? We had a two-layer problem where we had a ray coming down through layer 1, traveling along the boundary at the velocity of the layer of the second layer, layer 2, and then traveling back up to the surface with the velocity of layer 1. We calculated the total travel time of that ray as a function of distance x and depth to the interface z and velocities v1 and v2. And that gave us this expression by simplifying. Adding up those times and simplifying, the total travel time is equal to some constant which is related to the depth of the interface, the velocities of the layers, and plus 1 over v2, which is the slope of a line times the distance from the source. So the time taken by a refracted wave follows this relationship. We can plot up points from our refraction survey, and they'll follow a pattern like this, where we have a steeper slope at first, and then at some distance, which is related to the arrival, where the refracted waves are the first arrival. They arrive before the direct wave. That happens at the crossover distance. So there's some steeper slope up until the crossover distance, and then some lower slope. Those two slopes are reflective of the velocity in the first and the second layer. The intercept of this second line here, which is related to v2 and related to the refracted wave, we can use that and the velocities of those two layers to give us the depth to the interface. So all in all, what have we gotten? We've done this refraction survey, we've gotten the depth to the two layers, we've gotten the depth to the boundary between the two layers, and the seismic velocities of those two layers. So that's actually a lot of information, given that we only have taken measurements at the surface. That's the cool thing about seismology, is it allows us to image things under the ground, given only measurements at the surface. Okay, thank you, and I'll see you in the next video.